All right, BC kids, we're looking at the ratio test today. This is one of my favorites because it's just kind of easy. You know you want to use the ratio test when you see what's called a factorial. See this exclamation point that's there? That's called a factorial. And so you need to, when you're looking at the ratio test, remember factorials. Let me show you what they mean. Say I had 5 factorial, 5 with an exclamation point. That would equal 5 times 4 times 3 times 2 times 1. And any factorial, if it's 3 factorial, then it's 3 times 2 times 1. So it decreases in order by 1. They're always whole numbers. And they come up a lot in nature, and like how many sunflower seeds there are, and seashells, and how seashells are made, and it's this whole there's a whole gamut for these factorial things. But for us, we're going to need them in this ratio test. So here's some strategies that you will see. These are the recall things. That if I have n plus 1 factorial over n factorial, remember how it decreases? So if I have n plus 1 as my first term in my factorial, then the next one's going to be 1 less. So n plus 1 minus 1 is n factorial. And then it would be n minus 1 and n minus 2 and so forth down the line. But check this out. If I have n plus 1 factorial over n factorial, you end up having things that cancel out. Excuse me. So your n factorials on the top and on the bottom, they can cancel out, and this equals just an n plus 1. That's going to come up in some of the studies that we do. Second thing that's going to come up is, remember, if you have like bases and you have their powers are being added together when you multiply them. So this is 3 to the n times 3 to the first. Because they're like bases of 3, I would add the exponents n plus 1. And what that helps you to do, look at this, I got 3 to the n's that cancel out, and I'm left with an answer of 3 to the first, which is 3. So there's some reducing strategies that we're going to be using as we do some of these problems. Okay, so here's what it says. Ratio test for convergence. If the sum going from 1 to infinity of a sub n has positive terms and the limit as you go to infinity when you take the n plus 1 term divided by the n term is less than 1, then the series converges. If it's greater than 1, it diverges. And if it's equals 1, it's inconclusive. You got to use another test. Inconclusive, try another test. All right, so let me show you some of these and how they work. Let's look at 2 series we already know. This guy here, if I were to remember, 1 over n, he is our harmonic series. When we studied P series, that he came up. He's a harmonic series, and if you remember, for him, he diverges. We know that. However, we're going to look at the ratio test and see how this works with the ratio test, even though we know that this guy's going to diverge. So it's just showing you a simple application. We're going to start out with a simple application of the ratio test and then grow to bigger things. So 1 over n, here's what it would be. I need to take the limit as n approaches infinity of the n plus 1 term. Well, think about that. The n plus 1 term is going to look like 1 over n plus 1. And then I have to divide that by, I'm going to put it this way horizontally, divide it by the a sub n, which is 1 over n. So I'm taking the a sub n plus 1, put an n plus 1 in for the n, divided by a sub n. Well, if I do that, think about that, the limit as n approaches infinity is going to be 1 over n plus 1, but remember, keep, change, flip. I'm dividing fractions, so I change it to multiplication and then multiply by the reciprocal, n over 1. Now, I'm not going to show you the long way this time around, and then eventually we're going to eliminate this beginning step and go right to this step when you get more comfortable with it. All right, so let's do this limit. as n approaches infinity, and it's going to be this, n over n plus 1. Well, think about that back to like horizontal asymptotes. I have the same power on top, same power on the bottom, so I take their coefficients. So this one actually has a limit of 1. And apparently that tells me that it's inconclusive. I need to try a different test. So this one is therefore inconclusive by the ratio test. So the ratio test didn't work for that one. However, we know it's a harmonic series and we know it actually diverges. So, but by the ratio test itself, which is what this section's about, it is inconclusive. Let's try another one. What if I have 1 over n squared? This guy is a p series, right? And his power is 2. 2 is greater than 1, p series test. Therefore, I know that this guy's going to converge by the p-series test, but that's not the section we're in. But just in case you were thinking about that, here it goes for the ratio test. It's going to be the limit as n approaches infinity of 1 over n plus 1 squared divided by n squared over, but divided by 1 over n squared. So it's going to be times n squared over 1. So if I put it together, the limit as n approaches infinity, I'm going to have an n squared on top, and I'm going to have an n plus 1 quantity squared on the bottom. N squared, top and bottom. I end up with 1 again, and therefore this one's inconclusive. And you might be saying, well, what good is this ratio test? And I'll show you. All right, so there's 2 situations where you're going to be applying the ratio test, but the ratio test may or may not work. If it comes out to equal 1, it's going to be inconclusive. Try another test. So let's take a look at the next one, number 3. And this one says, using the ratio test, find the convergence or divergence. So here's what we want to do with this one. We want to take this guy and we want to rewrite it with n plus 1s. So anywhere you see an n, it becomes an n plus 1. Limit as n approaches infinity. So the first thing I have is an n plus 1 squared. That's this guy. This guy is going to be, think about this for a second, if I change this to n plus 1 and then plus another 1, it's going to be 3 to the n plus 2 over 5, n turns into an n plus 1, times, keep change flip, 5 to the n over n squared 3 to the n plus 1. That's the original just flipped. So then I want to think about, well, any of these exponents that are binomials like that, you want to take them apart. So here's what I'm going to say next. The limit as n approaches infinity of n plus 1 squared times 3 to the n times 3 squared. Remember, it's like adding the exponents. When I break them apart, I'm multiplying them, the like bases. This is going to be over 5 to the n and 5 to the first. Did the same thing on the bottom, times 5 to the n on top, n squared, and then a 3n and a 3 to the first. Whoosh, lots of changing things around a little bit. So let's cancel what we can cancel. I have a 3 to the n on top, 3 to the n on the bottom. I have a 5 to the n on top, I have a 5 to the n on the bottom. I have a 3 squared over a 3, 9 over 3. So I can cancel this guy, one of those 3's on top with that whole thing. 9 over 3 leaves me a 3, there it is. All right, now I'm just going to rearrange stuff. Canceled what I can cancel. Keep the n's together, n plus 1 quantity squared over n squared. Times, what else do I have up top? I have a 3 on the top. I have a 5 on the bottom. That's this guy here and this guy here. That's everything else is canceled out. I know the limit of this part is 1, n squared over n. So I get 1 times 3/5 gives me an answer of 3/5. Well, if 3/5 is less than 0, I'm sorry, less than 1 from our box up above, then I know that this thing converges by the ratio test. So the ratio test isn't always going to be inconclusive like those first couple examples look like. So when you see exponents that can be separated, that's a clue for the ratio test. That's one of your clues. The second clue is if you see a factorial. I said that earlier. If you see a factorial, you want to think about this ratio test. So let me show you how this one would work. The limit as n approaches infinity. It doesn't hurt any that they told you to use the ratio test, but anyway, if you were looking at it, the factorial tells you that that's a good choice. This is 4 to the n plus 1 over n plus 1 factorial, and then flip the original, n factorial over 4 to the n. Split up any powers, bases, and such, so you can see if anything cancels. This is 4 to the n, 4 to the first. This one's going to be n plus 1 and n factorial. I showed you up above how that thing works. It's always 1 less. So n plus 1 minus 1 is just an n factorial. Leave it that way. Don't go any further because it's going to cancel with this n factorial that's on the top. Cancel up what you can cancel, 4 to the n's, n factorials. What are you left with? You're left with the limit as n approaches infinity of 4 to the first, 4, over n plus 1. If I put an infinity into here, then I have a very large denominator, and so therefore I'm going to have this thing equal 0. Well, 0, the comparison is less than 1, and so I know that this guy converges by the ratio test. Do you have to say each time what test you're using? And the answer to that is yes, you do. All right, there's one more example problem, and then we'll look at maybe some practice problems. All right, here comes the first example last example problem. Get it on the screen for you. There it is. All right, so this one is a factorial. There you go. We're going to then use our factorial ratio test. If I do, think about this for a second. I'm going to go off to the side here. If I make this n plus 1, then it would look like this, right? 2n plus 1. Well, what is that really equal to? And you say 2n plus 2 factorial. Okay, so when I put the n plus 1 into that numerator, that's what I'm going to end up with. So I'm going to put my test together, limit as n approaches infinity, of 2n plus 2 factorial over n plus 1 to the 5th times, flip your a sub n to the 5th over 2n factorial. All right, let's see what we got. The limit as n approaches infinity. If I have 2n plus 1 or 2n plus 2 factorial, then it's 2n plus 2 is my first term. The next term is going to be 2n plus 2 minus 1, or 2n plus 1. And then the next one's going to be 2n plus 1 minus 1, which is just 2n factorial. Now you see that's where you're going to stop because that's going to cancel with that bottom guy. All right, so that's my first numerator. And then I have the n plus 1 to the 5th. I'm not going to change anything with that. Times n to the 5th over 2n factorial. So let's see what we're left with. I've got my 2n factorials cancel out, and pretty much that's it. So let me rearrange it just a bit. The limit as n approaches infinity. I have an n to the 5th over an n plus 1 to the 5th. See how they're like each other? So I'm going to put them together, and I still have, that leaves me with 2n plus 2 and 2n plus 1. Can't do anything with those. All right, so I know that the limit of this piece here equals 1. Right, end of the fifth over end of the fifth, so I'm going to have 1 times. And then I have, let me do it this way. Let me keep it in my limit talk. The limit n approaches infinity of, this is going to be, this piece equals 1, but I still have 2n plus 2 and 2n plus 1. What happens if I put an infinity into those? 2 times infinity plus 2 times 2 times infinity plus 1. However I look at that, that's still going to be infinity. And infinity is greater than 1, and therefore I know that this guy diverges by the ratio test. So there's an example of one that would be divergent. All right, a couple that I picked for us to look at. First one is number 4. What are all the positive values for p for which this series n to the p over 7 to the n will converge? Well, let's supply this ratio test to that and see what happens. The limit as n approaches infinity for n plus 1 to the p power over 7 to the n plus 1, all right, times, flip it, 7 to the n over n to the p. Separate anything you can separate so that you can then see if anything cancels out. I have n plus 1 to the p. I have on the bottom a 7 to the n and a 7 to the first. 7 to the n over n to the p. I can have my 7 to the n's cancel. Now I'm left with the limit as n approaches infinity for, rearrange it, put your n's together, n plus 1 to the p over n to the p. And then I still have a 7 on the bottom, 7 to the first on the bottom, so times 1/7. And since 1/7 is less than 1, then I know that this thing converges by the ratio test. But what does that mean about my p's? And so if I go back here and I look at it, my p's have to always be a positive value, because if they went negative, then I could have a situation where you would not have, you would not be able to converge. So it turns out that my p's, if you look at it this way, this was a bit of a confusion point in class, but when I wrote it this way, the kids seemed to understand better. Let me show you. If I write it as the limit as n approaches infinity of n plus 1 over n to the p power times 1/7. In order for that to always stay less than 1, then my power p has to always be a positive number. And so it has to be p is greater than 0. So this seemed to make more sense to most of the kids, that if you have a power there, the power has to be greater than 0 in order for that to be able to be a 1/7 for it to converge. So that's the first one that I want to show you, and there weren't a whole lot that I really wanted to show. Oh, number 7 was the next one. We'll probably stop with this guy. Number 7. I'm picking ones that are a little bit different than just the traditional type of thing. So here's the deal. If a sub n is positive, greater than 0, for all n, the limit as n approaches infinity for the n plus 1 term over the nth term gives you 6. Which of the following series converges? All right, so what I did was I thought about what each of these would happen to be. So if I look at this first one, a sub n, a sub n is positive, and so you know if that's the case and I put in an infinity into this thing, it's going to be an infinity. So this guy's going to be infinity, it diverges. If I go to part B, let me come to part B here, and I've a sub n over n to the 7th, that's going to give me something that looks like this. The limit as n approaches infinity for a sub n plus 1 over n plus 1 to the 7th, right, times n to the 7th over a sub n. So I'm going to rearrange it, put the n's together, and that's going to give me an a sub n plus 1 over a sub n times n to the 7th over n plus 1 to the 7th. Well, we know that this is equal to 1, right? N to the 7th, n to the 7th. What do we know that this is actually equal to? This took a few minutes in class for the kids to actually think about it, but let me curl up here. Whoop. That value equals 6. So I have 6 times 1 gives me an answer of 6, and 6 would be a diverge. 6 is greater than 1 in the ratio test, so this one's a diverge. What am I looking for? I'm looking for where it converges. All right, so let's try C. It didn't work for A or B. Let's do the same thing. It's a sub n. Now it's 7 to the n rather than n to the 7th. So let's see what that's going to look like in my ratio test. I get a sub n plus 1 over 7 to the n plus 1 times 7 to the n over a sub n. I'm going to rearrange things. I have an a sub n plus 1 over an a sub n. I have a 7 to the n on top. I have a 7 to the n and a 7 to the first on the bottom. So I know that these guys cancel. And I know that these guys equal 6. So I get an answer of 6. Actually, all my top is 1, right? So 6 times 1/7 and gives me 6/7. Well, 6/7 is less than 1. And therefore this one converges by the ratio test. So it says, which of the following series converges? I'm done. I figured out the guy that converged. I don't even have to check part D. All right, that should do it for the ratio test. I'll be back to talk about conditional and absolute convergence in the next lesson. Shoot me an email with any questions and I'll talk to you soon. Bye.